We are into our second hour of lecture 1. The topic is sampling, right? Yeah. So yesterday we ended up on this slide, and we have shown that the sampling effect. Let's still draw a few sketch first. So we introduce a signal that consists of spikes, which are equally spaced, and the spacing, of course, is the sampling period, right? So we introduced this an extension. So this signal has been introduced, and we call it S of t. And we have shown that this is kind of, as a matter of fact, we know that S of t is going to be preserving its shape after Fourier transform. So the result in the frequency domain is spectrum still looks like a series of delta functions that are spaced by 2 pi divided by t. That's the spacing in the frequency domain, right? So I was also trying to introduce to you that you can somehow write this expression. So back in the time domain, S of t, of course, this is already S of t, but you can also attempt to derive its Fourier series expansion. Fourier 级数展开. Why? Because it is a periodic signal. Any periodic signal we know can be expressed in terms of its Fourier series expansion. And that's the result. If you attempt to do that, you will get this result, which I'm going to copy right here. I claim that you can write this equation with a sum over k, and we have all the periodic component exponential j, almost running out of space, but anyway, 2 pi divided by t, small t, right? This is a Fourier series expansion. In the most general case, we should have coefficients. Fourier series expansion for any arbitrary periodic signal, you express it in terms of this summation, but there should be coefficients. But in this case, all the coefficients are equal. That's the idea. All the coefficients here, either here or appearing right here, they all equal to the same thing, which is outside 1 over t. That's a Fourier series coefficient. Okay, so far so good? Yeah. So this is a Fourier series expansion. Let me just write it down. Yeah. And the reason we can do that is because this signal in continuous time is a periodic signal. And also you can even introduce this symbol, omega s. Basically 2 pi divided by t can be denoted as sort of the fundamental frequency, if you will, of Fourier series expansion. Anyway, so let's make this definition. Omega, we'll come back to it will become useful. Why is it useful? Because later then, if we agree that this is an equality that which holds, 如果等号真的成立的话, if it really holds, 等号真的成立的话, then in a few steps, you can reach a conclusion that now xs, this is defined by, that's the spectrum for sure, and it's a Fourier transform of the signal that we're interested, multiplied by S of t, multiplied by that, okay? So when we multiply that, that's equivalent to sampling. This is equivalent to sampling, then we go to the frequency domain, and because of linearity, we can take a summation outside, from here to outside, Fourier transform. And then following that, for each term here, we could apply the shift theorem, right? So then we reach this final expression right there, which I'm also going to copy. The result of the spectrum after sampling. Spectrum after sampling is what? 1 over t being the same coefficient. Then still summation over k, and the original spectrum shifts it to the right and to the left. Shifted to the right, to the left by how much? By k times exactly this frequency. Okay? Okay, so we're going to leave this here, and so that's where we were at yesterday. And today, let's look at what's going on in the frequency domain by sketching. Okay, let's make some drawing. All right, so let's make a sketch of this is equation 3. Okay, so I'm going to use this part of the board. Yeah. So, but before I do that, let's still, just also draw a sketch of the signal of our interest, which is denoted by a continuous time. C stands for continuous, right? So this is our signal, and when we multiply signal with S, when the two of them multiply together, we still get a series of spikes with their height modulated by the amplitude of our signal. Okay, so that's the result, and we call this X sub S after sampling. Stands for sampling, right? And now we know that its spectrum should have this expression, this very expression, which there's a summation. Okay, so shifting to the right with the left, and they will also overlap. They overlap and add. So let's draw a few sketches. I think I'm going to need some other colors. So let me grab a few chalks. Let's assume that, all right, so the original signal has a band-limited spectrum. Okay? Assume that it's band-limited. And so, maybe just draw an arbitrary triangle with equal side, emphasizing the symmetry. Okay, and let's assume that the bandwidth is, let me be consistent, 2 pi b. Because omega, 2 pi b, right? 2 pi, and minus side, on the negative side, this is the frequency axis. So let's assume that this is our spectrum before sampling. Okay, before sampling. So this, that's that, right? So far, so good. And after sampling, because of that summation, we need to move this spectrum to the right and to the left. By how much? By 2 pi divided by t. And multiples of that. Right. So let's assume that, for example, let me just extend this really long, okay? It's a long line which extends to infinity on both sides. So let's assume that this is 2 pi divided by t, which has been denoted as big omega sub s, the sampling frequency in radian per second. Okay. So far, so good? Yeah. So let's assume that the sampling frequency in radian per second is right here. So that means we are going to, because of that summation, that expression, right? Because of that, we will have another copy right here of exactly the same shape, the triangle, which is illustrated by a triangle right here. So I'm trying to draw the same triangle, more or less, right? So that's over there, a new copy. Okay. Actually, I should change another color. So this is now another color. Okay. That's one extra copy of the band-limited spectrum, but now move to the right, and also to the left. Okay. So and also to the left. So let me just draw a dashed line right here. Something like right here, maybe. 2 pi divided by t with a minus sign. Okay, everything should be symmetric. Right here, that's another copy. And theoretically, here we also get yet another copy. We get yet another copy right here. You see, because that summation over there, if you look at that summation expression, right? K summation over k extends to both sides. So we got yet another copy with the same shape, more or less. And extension goes on to both sides, right? So that's a result of, in this case, we have a spectrum the bandwidth is 2 pi b, and sampling rate is 2 pi. Basically, this is sampling rate. It's actually 2 pi times sampling rate. Okay, 2 pi sampling rate over here. Bandwidth is 2 pi b, and then in this case, we have a kind of a we are good. Okay, in this case, we are good. Why? Because even though we have one extra copy, do the two of them overlap? They don't overlap, 没有重叠, right? They don't overlap. So still the triangle, they don't interfere with each other. There's no interference. So we're good. So the remark, no interference, we are good. There's no interference, so that's okay. But let's look at another case. What if now still sampling rate is right here, omega s equals to 2 pi sampling rate, okay? Depending on if your unit is radian per second or your unit is hertz. DC right here, 0 frequency. So that's the frequency axis. DC right here. So still, let's now assume that we have another signal. Another signal, XC, and its spectrum is slightly wider. Let's call it wide, W. Wide, a wide spectrum, a signal with a wider bandwidth. Okay? Yeah, let me just, you know what I mean. I don't need this symbol. Another signal, okay? Another signal whose spectrum is different. Let's assume that its bandwidth is wider and shape in general is also different. Let's assume that now the shape is like that. A wide band signal. And still we sample this signal with the same sampling periods. Therefore, in the frequency domain, this spectrum is also going to be shifted right and to the right and to the left, right? So at the same sampling rate, now it's shifted to the right. Now we get this extra copy right here. Da la 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 la. Right. Something like that. Yeah. And again, at 2 times, similarly, you get yet another copy right there and right there. And also to the negative frequency side. Let me just finish my drawing. Okay? Right here, right here. Okay? So that's a situation when we use the same sampling period for a signal that has a wider bandwidth. But now, in this case, we are in trouble. Okay? In this case, we have a trouble. What kind of trouble? The trouble is now, right here, the white and the yellow, the two of them now superpose with each other. They overlap, right? And wherever they overlap, they sum up, okay? They will sum up. So in the frequency domain, there's overlap. So these two spectrums are going to sum up. And the result, the sum could be like that. That's a sum. And also here, that's a sum. And also here. Actually, this spectrum is periodic after sampling. All right? And we say that we know that we're in trouble. Why? Why are we in trouble? Because compared to the first case, this first case is a Fourier transform. Remember, it's a Fourier transform of this series of spikes, right? This is a Fourier transform of our signal after sampling. Sure, it looks different, but then the middle part is still preserved. The middle part has the same shape, it's not affected. The middle part preserves its shape, its spectral shape, right? So what we need to do to reconstruct the continuous time signal is pretty simple. Let me just mention, you might have learned it elsewhere, but let me just agree on that. What we need to do is just to apply a low-pass filter right here, right? If you ever apply a low-pass filter, an analog low-pass filter, then ideally we can reject all the extra copies and retrieve back our middle part. We can get it back by using a low-pass filter. We can get it back. Okay, this shape is there by using a low-pass filter, and we come back to that in our next lecture. Okay, so we are in good shape. We are fine. After sampling, there's no overlap between components. Okay, so we can easily get back the middle part by using a low-pass filter. Okay, and you say, if you will, the low-pass filter, its cutoff frequency, for example, can be set at half of the sampling rate, which is pi divided by t. Okay, and right here minus pi divided by t on the other side. Okay, pi. So we use a low-pass filter. Now let me write it down. We are fine because we can apply a low-pass filter to get back the middle part. That's the original signal. Okay? The signal is not distorted. The signal is not lost. Still, signal. The information is still over there, right? But in this case, when we sum up, I kind of hesitate to really say that now green is white plus yellow. I kind of hesitate. 我犹豫啊. I hesitated to say that the green is a sum of yellow and white. The reason is because, let me mention, actually, the spectrum have complex value. We have Fourier transform, right? The result of Fourier transform is, in the most general case, they're all complex numbers. Spectrum belongs to the complex domain, right? So ideally, I should just draw the kind of the real part and maybe use another dimension to draw the imaginary part to be the most rigorous. But we don't bother to do that. Okay. So, but anyway, you know that in this frequency range, this part of the spectrum is going to overlap with that part of the spectrum, and we are in trouble. Okay. Can we still apply the same filter to retrieve the original shape? Can we use the same filter and retrieve this original spectrum, which looks like this shape? We cannot. Do you see what I mean? Yeah, we cannot use this low-pass filter. However ideal it is, apply a filter, you don't get back the original spectrum. So that is to say that the yellow part is being confusing. Yeah, it's being added on top of the white part, and we call this aliasing. Okay, aliasing, because this part, if you will, that's the high frequency. The high frequency now, I say they are confused. They're mixed up with the low frequency. They show up in a wrong place. This part of the spectrum shows up in a wrong place, at the wrong place, and they are going to mix with what's original there to confuse us. So the best we can do is to apply a filter, perhaps right here, but then you lost this part. Okay. Now, if you apply the same filter, you will lose this part. You lose everything that is higher than half of the sampling rate. They are permanently lost. Okay, so that's why so we can compare these two different cases: narrow bandwidth, wide bandwidth. Whenever the bandwidth has anything above half of the sampling rate, then they're in trouble. Then we are in trouble. We will lose them after sampling. We will lose this part of information after sampling. Okay, so that's a sort of a simple sketch for what's going on in the frequency domain. Okay, yeah. So far, so good. All right. Yeah. Okay, so that's why. So I'm making a suggestion that now by observation, by this simple sort of drawing of this sketch of the equation, we can reach a conclusion that we want to ensure that our sampling rate is bigger than 2 times the bandwidth. The engineering conclusion that, well, now if you know your bandwidth beforehand, for example, if you know your bandwidth is 20 kilohertz, then make sure your sampling rate is at least 2 times higher, 40 kilohertz, right? So if your bandwidth is 1 megahertz, if you know that beforehand, you want to plan to use a sampling rate that is at least 2 times higher, say 2 megahertz, at least 2 times higher, to ensure that after sampling, nothing is going to be aliasing. There will be no aliasing. Okay, we'll be in this situation where these triangles don't overlap, then we know we are still good. We know we're still good. Okay, so that being said, we want to ensure that the sampling rate is greater than 2 times the bandwidth. And here comes a historical question. I say historical question, right? This really has happened in history, or is still happening. So let me say, for example, what if the sampling rate of our system is 8 kilohertz, and somehow it has been defined by your boss or by the government or by a universal standard? Our system is going to have, is recommended to obey the standard to have a 8,000 hertz sampling rate. I say it happened in history. But what if somehow you have a signal and its bandwidth is around 6,000 hertz? What should we do? Do we change the system? Do we change the signal? Right? Because we really hate aliasing. Okay? So you need to compromise. Either convince your government, hey, 8,000 hertz is not enough. We need 12,000 hertz, 12,000. Do we convince our government? Do we convince your boss, your company? Or do you just change the signal? Opinions? Let's vote, all right? Anybody for changing the system? Changing the system, anybody? Changing the signal, anybody? Changing the signal. You guys are good students. You are not maverick. 不够反叛. I will start my own company, right? We go for 12,000. Right? Okay, so historically it happened, okay? It happened where? It happened to landline phone communication, telephone, traditional telephone, right? So you dial the telephone. Have you seen the, anyway, telephone, yeah. So many years ago, when they defined the standard, so they set the sampling frequency to be 8,000 hertz for speech communication. But the problem is, for most of the speech component, we know that it's fine. Most of our vowels, 就是母音啊, R, E, U, or the vowels, most of the energy indeed concentrates below the half of that. Half of that is 4 kilohertz. Okay? Most of our speech signal has an energy that concentrates below 4 kilohertz. But there is exception. I was talking about vowels, right? But for consonants, 子音, like non-vowel sound, sometimes human speech can go beyond 4 kilohertz. You can see that in fast Fourier transform. Okay, you see those components. And the best example I know of is 2 sounds. The F sound, F, and the S sound. So we will be in trouble, FS, okay? Next time when you try to talk on the phone, okay, to your friend or to your parents, do the test. Try to say S or F and make them guess which one are you talking about. Which one are you saying? I say it's hard to distinguish because the S has a lot of, when you make the sound of S, there's high frequency component, okay, because of turbulence, the way the air flows. So the sound airflow goes beyond 4 kilohertz. Typically, we see, in my experience, we typically can find them around 6,000 hertz for sure. Yeah. Everybody can do that. If you can say S without going beyond 4 kilohertz, let me know. You need to see a doctor. Okay. So S or sh, yeah, such kind of sound. Indeed, they go beyond 4 kilohertz, beyond the Nyquist rate of phone communication system. But somehow in history, they cannot afford. There was a long time, yeah, probably before you were born, yeah. A long time, somehow the standard is there, 8 kilohertz. So that's why when you need to really say S or F, good luck. Okay, so there's a. Have you heard of alpha, Charlie? C is for Charlie. What? Like in the Navy, naval communication, they invent or avian communication, 航空或者航海 they invent names for all the letters. I just remember C is Charlie. I forgot everything else. D may be darling. I think D is darling, C is Charlie. So you need to really say a word to avoid confusion, to avoid this kind of confusion, F or S. It's pretty difficult. Okay? So historically, you guys are right. People just compromised. They say we just low pass the signal. Okay? Still, we hate aliasing, right? They hated aliasing. We still hate aliasing. But our solution, the historical solution, is to recommend that we apply a anti-aliasing filter. Did I write it down? Write down. Yeah. The historical solution is that we will apply an anti-aliasing filter even before we start digital signal processing. Okay, apply a low-pass filter analogically in the analog domain to ensure that our speech signal does not, after filtering, does not contain any component that is higher than 4 kilohertz. Historically, that's what's been done. Okay, anti-aliasing filter, but still, now we can just officially go through this theorem. The important theorem. To summarize our observation, there's this famous theorem by the name of Nyquist-Shannon sampling theorem. Two great guys, Nyquist-Shannon, and you can find the theorem on the textbook. So I'm going to read it once for now. So we suppose that we have a signal right here, and its Fourier transform is denoted as big X, small x in time, big X in frequency. And now next, I suppose that there exists a band limit. Okay, there exists sort of the bandwidth which is finite, a finite bandwidth such that our spectrum is all zero beyond this bandwidth. Is that clear? I'll stop for a while for you to ponder upon what's the meaning of this sentence. Suppose that we do have a signal and the signal has a finite bandwidth. The bandwidth is no bigger than omega sub n. N stands for Nyquist, the name of this scientist. Okay. Suppose that the bandwidth of our signal is below Nyquist rate. That's the meaning. Yeah? Anything above that frequency is going to be all zero. Okay? Nothing beyond omega n. Suppose there's nothing beyond omega n. That's the meaning. Okay? Then what? Then we say the signal can be uniquely determined by its samples. As long as we sample at a sampling rate that is 2 times higher, that is at least 2 times higher. Okay, yeah. You have a bandwidth. Make sure you sample your signal with a sampling rate that is at least 2 times higher. That's the meaning of this sampling theory. Why? Because later you want to sample at a sufficiently high rate so that your signal can be reconstructed. That's really the meaning. This is sort of a jargon, a mathematical way of saying things, but really it means that so that if you sample with a sufficiently high rate, then you will be able to uniquely determine your signal from the sample. Okay, so that's what the theorem is about. You will be able to, in principle, in theory, your signal can be reconstructed. Okay, there will be no ambiguity, no aliasing, no confusion. Okay. All right, so far so good. Yeah, this is on textbook. Okay, the theorem, and we will just to yes. Let me also mention that we will next then discuss how to uniquely determine, how to make the reconstruction. That's the next topic. But at least we know that theoretically it's doable, it's possible, as long as we sample at a rate that is sufficiently high. How high? At least 2 times Nyquist. Okay, 2 times your bandwidth. Okay, any question right here? 可以吗？わかる？We have yeah. Anyway, so I'm pretty sure this is a clearly stated theorem on the textbook, and we'll talk about how to uniquely determine how to get back our signal by low-pass filtering. The way we are going to recommend is to apply a low-pass filter with a cutoff frequency right at Nyquist rate. Okay, so we'll do that maybe next week or in a moment. We can start doing that from today. But then I do have a few final remarks before we end this lecture. Okay, this lecture is about sampling, but I haven't mentioned that most of the time, first, we usually assume that, at least in this course, okay, in this course, I usually assume that our signal is real valued, no imaginary part. Okay, the signal when I write down a continuous time signal, or even a discrete time after sampling, right? Our signal is assumed to be real unless we mention otherwise. All right, so can you agree with me? Unless I mention otherwise, unless you mention otherwise, we agree that we assume our signal, just for simplicity, every signal in the real world is real valued. Okay, no imaginary part in the time domain. Okay, so that's just a statement. But then following that, consequently, if you have a signal, a real value signal in time, then what happens in the frequency domain? In the frequency domain, we will have a symmetry. We do have a symmetry. Okay, we have a symmetry in that some of you might be familiar, but let me just, for the sake of being comprehensive, let me just mention. If X is real at all t, then a spectrum evaluated at the negative frequency basically is going to be the spectrum evaluated at a positive frequency with a conjugate. So I didn't exactly say that, but because of this symmetry, it can be easily shown from the definition of Fourier transform. This is a fairly trivial property, okay? So I want you to make sure that we all know that. And because of that, then if you take the absolute value, we're talking about the magnitude spectrum. Okay? The magnitude spectrum is going to be symmetric around frequency 0. Because complex conjugate has the same absolute value, right? And you can also just further the angle of our spectrum at a negative frequency should be the minus sign, with the minus sign times the spectrum at the positive frequency. Okay, so we have these properties, these symmetry properties, because we make this assumption, right? Because of that, only true if we talk about a signal that is real in the time domain. So these two are pretty straightforward. The final remark I want to make right here is an interesting fact. Okay, interesting fact. We talk about, we have a signal and you want to know its bandwidth, right? Bandwidth of speech, bandwidth of anything, right? You want to know the bandwidth first, and then, if possible, design your system with a sampling rate that is sufficiently high, at least 2 times higher than the bandwidth, right? The problem, I have a theoretical problem right here, which is my own, 我自己小小心得啊。This is my own comment, interesting fact. It turns out that mathematically, a band-limited signal cannot also be time-limited. It's impossible for a function to be both limited, to have a limited bandwidth in frequency as well as a limited time duration in time. Duration 长度啊，时间长度 length in time. Okay, mathematically it's impossible, and we can prove that. Okay, later in the semester if you're really interested. It's actually, we talk so much about assuming that you know the bandwidth, but I have a small problem right here. Mathematically, it's impossible for any signal with a finite duration to have a finite bandwidth. Mathematically. And that's my small problem. And that's not going to be useful. 就是 in Chinese we say 知道对人生也没有帮助. It's not going to help your life, okay? But I think it's a funny fact, right? It bothers me because we really talk about band-limited interpolation, band-limited signal, but no such signal can exist with finite time. And we have a trouble because in the universe, in your life is finite. Your time at NTHU is finite. Your time taking this course or taking an exam or making any measurement is finite. Right? The universe is finite, if you will. So it's more interesting fact for us to ponder upon. But with that, let's just finish this first lecture. And I would like to take a brief sneak preview. 稍微看一下. Let's preview the next lecture, which I have also uploaded to e-class. Okay, you can find them from the system. But let me switch to the other lecture. Let's take a 2-minute break. Oh, yeah, we don't have time. We do. We have about 10 minutes, right? Yeah, good. Let's take a 2-minute break while I make the switch. Can you find it? Yeah, this. Oh, by the way, are you familiar with this overleaf?